Hello all and welcome back to this course on digital systems. So the last couple of lectures we looked at the elementary D latch and a D flip-flop which had one input, one output and one clock, right? And this was constructed purely with inverters. Now the question is, can I implement these storage elements, right, or these programmable delay elements that we defined as flops and latches using other gates as well? Okay, so so the obvious choice for us is, can I implement something using AND gates, right? Let's just, it may be a very trivial question, but let us just ask ourselves this question, right? So suppose I implement something like this, right? Is it even a valid is it even a valid system, right? Or is it a valid circuit that will hold the state for me? Well, the answer here is no. Remember, when we discussed the inverter, right, we said that ultimately the state has to be held using back-to-back inverters. So, and we also described in great detail about why the transfer characteristics, basically when you superimpose the true transfer characteristics, there are only two states which are stable, the 0, 1 or 1, 0. So if this is 1, this is 0, or this is 1, this is 0, right? So this back-to-back state is very important, and when you don't have an inversion available, like in the case of an AND gate or an OR gate, this whole back-to-back connection makes no sense. Okay, so if the input is 1 here, then the output has to be 1 here, and you'll have there's no way that you can hold that state, right? So the inverter, again, the inversion is very important in order to hold this state for us. Okay, so that's why you will see that any alternate structure of the latches will either be done with NAND gates or NOR gates. Of course, like inverters, right? You need that inverting gate in order to hold the state. So let us analyze this structure now. Okay, this is just two input AND gate, NAND gates, whose outputs are now cross coupled. Okay, I am taking the NAND gate of let me call this N1, N2. Okay, I am going to call this Q and Q bar. Okay, so Q is fed as input to NAND gate N2. Q bar is fed as input to NAND gate N1. Okay, now I can label these two inputs as, I will just call them A, B for now. I'll give them more meaningful names in due course of time after the discussion, right? It will become evident why we are calling it that after that, right? So now, in order to analyze this system, right, what we first of all need to do is, we need to first identify what is the configuration in which this structure can hold the data. Remember, ultimately the cross coupled structure is supposed to hold data for you. Now you have two NAND gates with the other input free, right? So when you make the other input as 1 to the NAND gate behaves like an inverter. Okay, so therefore if you look at this structure here, okay, it's basically like this. I can redraw it like this. Right, I am going to call it like this. Both I am going to assume is connected to VDD, right? This output is fed as input to this. This output is, so if you look at it, I am actually drawing it like this, N1, N2. Okay, now you see that this is very similar to this cross coupled inverter thing. And in fact, the NAND gate N1 and N2 are going to behave like inverters when the other inputs are tied to 1, right? And therefore, this can definitely hold the state for us, right? So therefore, you know, if I want to describe this gate, right, I'll just write this. I have two outputs now, Q and Q bar. Okay. So if I assume that A equal to B equal to 1, right, then it is going to basically keep this in no change state, right? Whatever, so this is Q and this is Q bar. So remember, in the D latch case, Q bar never came out. Okay, that node was not exposed. So we said it had only one output. In this case, we are saying that node is also available to the outside world, and therefore this is a 2 input 2 output system. Okay. Now let us analyze what happens when I have the input A equal to 0 and B equal to 1. Okay. So let's say this is 0 and this is 1. The thing with a NAND gate, if you remember the truth table, if any one input happens to be a 0, the output will simply go to a logic high, right? And therefore, if A equal to 0, then Q also will go to 0, Q will go to 1 instantaneously, right? That's because of the NAND gate, right? Now, if Q goes to 1 and the input to N2, therefore, both the inputs to this N2 NAND gate are going to be 1, right? And that means this has to go to a 0 state, right? So what will happen effectively is you are going to have a combination that can force the output to go to this state 1 0, right? So in fact, it does not matter what the previous state was at that point, right? Now at this point, note that if this goes to 1 1, right, let's say both A and B go to 1 1, then it will simply continue to hold the state for you. It will just hold it as 1 0, right, because I just told you that's a no change state, right? So this one is if A equal to 0, B equal to 1. Okay. Now on the other hand, if A equal to 1, B equal to 0. So let us look at that. I am going to write this in red. Okay, I am going to write this in red. If A equal to 1 and B equal to 0. Okay, I will write this as thing, right? Then it's quite obvious, you have to analyze it the other way around. 0 is going to N2. Any one input to the NAND gate happens to be a 0, then the output of that NAND gate will simply go to a 1, right? Now N1's input is going to be 1 1 and therefore this output will be 0. So therefore this will be 0 1. Okay. And now again, if A and B happen to go back to 1 1, it will simply hold this state as it is. So this is if A equal to 1 and B equal to 0, right? And what this effectively tells us is, unlike the D latch, we are able to sort of set or reset the output to the known state that we want, either 0 1 or 1 0, by just controlling these inputs directly, right? And therefore we are able to get this whole thing to work as a set reset flop. So this is going to be called a set reset latch. Actually, it's not a flop, it's a latch. Okay. So therefore, I am going to now call these two inputs not as any A and B. I am going to basically call it S and R, which is reset. Okay, SR is what I will call it here. S and R, right? And therefore, this is in short is called an SR latch. Okay. Now what happens when I consider the other case. So we have looked at the input combination of S and R being 0, 0, 1, 1, 0 and 1, 1. So let us now look at the condition when the inputs S and R are both connected to 0, 0. Okay. The problem with the 0, 0, okay, is let us look at this condition. If it is 0 and 0, and then automatically, because it's N1, N2 are NAND gates, the output will go to 1, 1. Now let's assume that both S and R make a transition simultaneously to 1, 1. That means you're trying to hold that state. Okay, so you have gone to the output Q and Q bar becoming 1, 1, and you're trying to hold that state, right? Because 1, 1, I told you, was supposed to be a state where you hold the data. Now the problem is when you go to 1, 1 state, remember the Q and Q bar were both 1, 1, right? So I'll just draw this condition out separately here, okay? Yeah. Right? And earlier, the previous output was, let's say, 1 and 1. Now what is going to happen? This is N1, N2, okay? Because Q is equal to, this is Q, okay? Let me write that Q, which is 1, right? Previous state, Q bar was 1, right? You are coming from the state 0, 0, input being 0, 0. So both were 1, 1. Now Q is 1, N2's input therefore has to be 1 and 1, right? And the moment you have both inputs to a NAND gate, N2 being 1, 1, this output has to go to a 0, right? So if this now goes to a 0, the 0 will come back to N1, right? And then it will cause the output here to go to this 1, 0 state, right? Because there's a 0 on that. Now on the other hand, if I analyze it the other way, right? N2's input is, output is 1, Q bar is 1, and therefore N1's input, both of them happen to be 1, 1. Then this output could go to, instead of this transition, it could also go to 0, 1. So what happens is, this becomes an indeterminate state because you do not know which of these two output states it will go and stop, right? It will go and hold any of these two output states depending on noise and other things as usual, right? And that is not in the control, and that is why this is an invalid input. Okay, 0, 0. It's not because the combination 0, 0 causes an in a wrong output. No, if the input is 0, 0, the output will be 1, 1. But the problem is, if you enter the 0, 0 state and then go to the 1, 1 state, right, then you have a problem. On the other hand, if you enter 0, 0 and then go to 0, 1 or 1, 0 state, S and R being 0, 1 or 1, 0, there will be no problem, because it will set and reset accordingly and then you can hold that state. But when you go from 0, 0 input to 1, 1 input condition, the output Q and Q bar can go to a random state. So this can be 0, 1 or this can be 1, 0. That's the issue, right? And this is really not in our control, and that is the reason the 0, 0 is considered an invalid state for this SR latch. Okay. Now, having constructed this with NAND gate, obviously I can also construct this with a NOR gate, right? Except that the condition can change a little bit. And by the way, this is actually our function table. Okay, and really note that it's a little more cumbersome than just a truth table, right? Because we really have to talk about from where we come, how we come and all that because of the state, right? So I have again, you know, S R, okay, Q bar. Okay, now how do we analyze this? Again, I told you the starting point is to simply analyze what is the condition in which this can hold the data. What is the no change condition? The NOR gate will behave like an inverter if one of the inputs to it happens to be a 0, right? And therefore, when I consider the case S equal to 0, okay, and R equal to 0, then this effectively, again this is NOR gate 0, NOR gate 1, right? Then this effectively becomes like this. This is 0, right? This is 0, okay, and I am going to connect this. So this is N0, N1, okay. So you have Q output, and then N1's output is Q bar, right? And therefore you are going to hold this data accordingly, right? This is N0, right? So you're going to hold this just with like a back-to-back inverter, and therefore if I go ahead and write the function table, you will simply start with S R Q bar. If I do 0 0, right, I am going to say this is the no change state, right? Now when S is equal to 0 and then it is 1, right? When S equal to 0 and then it is 1 and R is 1, right? Then we are talking about the case when, so let us look at it. So the NOR gate is when any one of the inputs happen to be a 1, the output will go to a 0, right? And that's why when I consider this, N1 whose input has gone to 1, Q bar has to go straight away to 0, right? And if that is 0, then you go up and S is already, S is now 0, Q bar is also 0, and therefore you will have Q going to 1, right? Now from this state, from 0, 1 state, if I switch my S and R to 0, 0 again, then it will simply hold this state as it is. Okay, this is if S equal to 0, R equal to 1 previously. Okay, this is the previous state. Now, if I now reverse this 1, 0, then I have to analyze this in exactly the opposite way. N0 is the NOR gate whose one input is 1 and therefore the output has to be 0 for this. Q will go to 0 and then you are going to cause, if Q is 0, then you have N1's input being 0 and therefore the output has to go to a 1. And now from here if I switch to 0, 0 state again, it will just hold this state for me. If S equal to 1, R equal to 0 previously. Okay. As was the case with our NAND based SR latch, the NOR based SR latch also has an invalid state, and that happens to be the 1 1 condition. Of course, I told you if you do 1 1, then Q and Q bar will go to 0 0 here. But from 1 1, if you go to 0 0, then this output can either go to 0 or 1 or 1 or 0. It can land up in any state, and therefore this is indeterminate. Sorry, if S and R happen to, from here you go to 0 0, correct. and therefore this condition is indeterminate. Right? Determinate, yes. So, and therefore you have to ensure that this combination of 1 1 does not occur when you are using this particular latch. That's the key idea here. Okay.